Okay, give me 1 second and we'll debrief.
Yeah. Okay, can you hear me well? Yeah. Okay. So yeah, hi everyone. My name is Eduardo, and well, there was a title change. This is the framework. So I'm going to talk today about HELIOPOLIS, which is a framework for verifiable computation over homomorphic encryption using interactive oracle proofs. This is joint work with Diego Aranha, Anamaria Costache, who is here in the audience, and Antonio Guimarães. Do I have a clicker? The clicker? It's this. Yes. Yeah, okay. Oops. Going back? Yeah. Okay. So first of all, what's verifiable computation? We have to aim somewhere? Okay. So verifiable computation, there's something going on with the slides. It's this problem, the animations disappeared, but anyway, where you have a verifier and a prover, or a client and a server, and you have the client send some input to the server who returns the output and the proof. And the goal is that the client, given the input, the output, and the proof, it should be able to check whether this program executed on the input actually returns the output claimed by the prover. Okay, the slides are really different. Okay, so here you should have soundness and correctness. So it should be the case that if a proof is false, the verifier should be able to reject. And if the result was the right result, then the verifier should accept. And what's the drawback? That we have no privacy here, right? So we are at the homomorphic encryption conference. You probably see what we are going to do to fix this problem. And I was talking about programs, but really in the domain of verifiable computation, what you have in all of these efficient constructions is like a model of computation that is based on arithmetic circuits, plus some tricks, some small tricks, but it's mostly arithmetic circuits. So whenever you want to run some sort of program, you need to go through this kind of compilation where you're going to express your program in terms of arithmetic circuits, and then you feed that into whatever proof system that you have in your backend. And the problem is that this proof system works over an arithmetic circuit over some ring, so you have to pay the cost of this sort of compilation. Okay. Yeah, homomorphic encryption. This is going to be quicker. Everyone knows what it is in this audience. But I wanted to just fix this kind of point of view of the commutative diagram. So whenever we're using homomorphic encryption, what we are really interested in is the top part here, right? We have some plain text, and we want to compute some circuit on them. But rather than going this way, we are going to go through this part of the commutative diagram because we want privacy. We want to encrypt the input so that whenever someone is computing over the ciphertext, they don't know over what they are computing. Okay. And this enables some series of applications. You can think about outsourcing computation. You can think about some software as a service thing. So again, this should be kind of familiar to the first slide on verifiable computation. You have some client sending some encrypted input to a server, returns the result, maybe applies some machine learning model. You have to do this these days. So the good thing about homomorphic encryption is that now we have privacy. We have encrypted the input of the client, but there is no soundness. We have no guarantee that whatever the server is returning is indeed the output. So what can we do? We have homomorphic encryption, gives us privacy but no soundness. We have verifiable computation, gives us soundness but no privacy. Let's put the two things together, right? So since the client is going to encrypt and decrypt by himself, let's put verifiable computation here at the bottom, and the problem would be solved. We are just going to check that this was done correctly, all these operations on the ciphertext. The problem is that when you look at the ciphertext space of homomorphic encryption, it's not very algebraic. Every time you're doing products, you're doing a bunch of operations like rounding, real division, and so on, that break the ring structure. They break distributivity, they break associativity, and things like this. So this is a problem because now you need to express all of these operations back, again, in terms of like an arithmetic circuit, and that's going to blow up the size of your circuit. So, facing, what can we do in the face of that problem? There's two different solutions. What you could first do is work with an algebraic structure that is as close as possible to the ciphertext space of homomorphic encryption. So you could work with the ring that is used for the ring learning with errors problem, rather than, with, not the ring, I don't want to say the ring, right? But rather than with the ciphertext space. So notice how we have like different subindices here. So now every time you need to do some non-arithmetic operations, so every time you compute a product of ciphertext, you are going to express these operations, this rounding, the real division, the mode switching, you name whatever you're using, as a set of gates over this other, the ring learning with errors ring. This is in fact the approach that has been taken by many works. So I have listed here just a few. There's also like 2-3 posters around here on the same topic. So this has been what we have been doing so far. The problem though is that all of these non-arithmetic operations, they are going to require a number of constraints, so a number of gates in your arithmetic circuit that is proportional to the size of the ring for ring learning with errors. So this is like, thousands of gates. It's like a really big ring. So you either do that or you give up on all these tricks. You give up on rounding, real divisions, and so on, and you get back to like BV. And the second solution is that you could try to verify the operations on the plaintext space. So rather than checking if what has been done on the ciphertext space is correct, what we really care about is what happened on the plaintext space. And this is what we do in this work. Okay? I have to mention also some concurrent work by Gargoyle and Wang, where they have like similar techniques, but they have a more general setting. They look not only at homomorphic encryption, but they also look at things based on discrete logarithms and stuff like that. But since they are also more general, they don't look so much about all these details that are necessary when you want to implement this with homomorphic encryption. And this is a big part of our work. OK, so it's horrible when you have no animations. So this box was meant to move up. So rather than having verifiable computation here, now we have verifiable computation there. And what's the problem now? Again, we need to have some algebraic structure in order to have all these proof systems that work with arithmetic circuits. So now our work is not able to support CKKS because it has the same problems. CKKS has all of these approximate arithmetic, and as soon as you have approximate arithmetic, you have lost your algebraic structure. You have lost distributivity, associativity, etc. for the product. So that's something we cannot support. Okay. Yeah, so now interactive oracle proofs. So this is something that's maybe not familiar to everyone, but just like very quickly explaining what interactive oracle proofs are. So I imagine everyone knows about MP here, right? It's your classic mathematical proofs. So you have a prover that sends a proof to a verifier who is deterministic and polynomial time, and it should be able to verify, whether this is correct or not. So we have soundness and correctness. And there's two different generalizations of the notion of MP. So you can have interactive proofs. When you introduce two new resources, the verifier interacts with the prover, and moreover, the verifier is now probabilistic rather than deterministic. You could do a different generalization where you have a probabilistic verifier, but rather than introducing interaction, what you're giving the verifier is oracle access to the to this proof. Okay. And then you have interactive oracle proofs, which put these two things together once again. So it's like a generalization where you have an interactive proof where every message sent by the prover is a PCP. It's a probabilistically checkable proof. So there's some challenge, comes an oracle, verifier does some queries, and so on. And why is it interesting to work with this model? It's because it's like an information theoretical model that is very useful whenever you want to compile and create some snarks, so some of these systems for verifiable computation. So there's a whole array of compilation techniques, but what's important here anyway is that, let me rephrase. Yeah, okay, so what's important here basically is that given an IOP, there's different ways to compile it into a snark. Each of them has different requirements, okay? So you have like Reed-Solomon coded IOPs, polynomial IOPs, delta correlative IOPs. And each of these can be compiled into a snark, and you have like different pros and cons. Again, like there's plenty of work here, not enough time, and also not fun when your slides are not working. So anyway, a lot of works on IOPs. What we do in our work is that we show how to modify IOPs to work on top of homomorphic encryption, okay? So I'm first going to explain the top part, what did we change there, and then I'm going to talk about the bottom part. So now the prover is going to work over ciphertext. The verifier is going to send encryptions of messages to the prover to do work on them. Now, since the prover is working on ciphertext, whatever the prover puts inside the oracles is also going to be ciphertext. So these are going to be like encrypted oracles. The verifier throws challenges which are still in the plaintext space because we are testing things in the plaintext space. And how does the verifier, retrieve the plaintext is because he has the secret key, right? So he can decrypt and see what was the query, the result of the query on the plaintext space. And given this, we are able, we can, all of the things that you can see here with the green check, we are able to port those compilers to the homomorphic encryption domain. This one we don't do, mostly because it's better if you do it this way, with these delta correlated IOPs. It allows you to get better parameters for this snark. But on the concurrent work, they claim that they can use this, and there's other people who told me that there's maybe an error. Do your own research. Okay. Next slide. Yeah, okay. And how does this work? You can maybe already see it coming, that the reduction is actually very simple from our encrypted IOPs to the normal IOP. Any adversary that breaks soundness here against this encrypted IOP, so against the encrypted oracle and given access to the key, can already break the soundness of the original IOP. So the reduction, it's really simple, and that's great because it also allows us to preserve many parameters of these IOPs with like a couple of details to take into account. So first of all, the length of the proof is going to blow up with the expansion factor of the homomorphic encryption, right? Because now we have ciphertext inside the oracles. Also, the number of queries is going to blow up because the verifier is really interested in some plaintext. But this plaintext is inside a ciphertext, and that ciphertext is going to pack a lot of stuff usually. So you need to take into account that if you're packing stuff, now you're also blowing up the number of queries of the underlying IOP. And this, the other exception is like, asymptotically, we would be done here, but no, in practice, there's many things to take into account to make this be actually, implementable and so on. So this is a big part of our work. I will talk about this at the end of the talk. Okay. Another important aspect is that we can preserve zero knowledge. And this is very useful in practice. Because now, the prover, rather than having like an encryption of the input or something like this, he could just have plain text, and this is going to greatly improve the parameters of your system. So rather than having ciphertext operations, you can have like ciphertext plain text operations. Of course, this requires to be careful. So in order to actually be zero knowledge, we need to have the homomorphic encryption scheme support some sort of circuit privacy. So you can think about this input of the prover specifying some constant addition, constant multiplication gates. And the other issue is about this query blow-up that I was talking about on the previous slide. So all of these, when you compile all of these IOPs into snarks, into all these verifiable computation systems, you can show that they are zero knowledge up to a given bound in the number of queries. And the verifier is now seeing a lot more than it would usually. Now, whenever he wants to get some plain text, he's going to decrypt a ciphertext, and there's a bunch of other plain text in there. So you need to be careful about that. And then there's also the question of whether the verifier is honest or malicious, because if the verifier was malicious, then you need to make sure that the ciphertext is well-formed, et cetera, et cetera. So these are different things to consider. Okay, so now we can talk about how we do this compilation. So all of those different compilers that we are considering, in practice at some point you have to do some low degree test or like a correlated agreement test. And in practice these days, this means using the FRI protocol. So the FRI protocol is an interactive oracle proof of proximity. And what it does is that it shows that this, the messages here in the oracles, basically they are well formed. So the prover is sending here some oracle where in theory it's a Reed-Solomon code word, for example, for Reed-Solomon encoded IOPs. So with FRI, when you're compiling this is that you're actually checking that that was the case. So same happens in these delta correlated IOPs and the others. So the good thing is that FRI is an IOP itself. So we can once again apply the same idea of we are going to have FRI where we encrypt the oracles that you send in FRI, and you're going to verify in the plaintext space. So the prover is running FRI again. Now you're compiling an IOP with another IOP, and you do the same thing all over again. You're computing on ciphertext, but the verifier decrypts and checks on the plaintext space. And another good thing about FRI is that it has been recently shown to be secure under Fiat Shamir. So we can make the whole thing non-interactive. Okay, and FRI is very scary, but you don't need to understand a lot for the purpose of this talk. So again, think this is the IOP. So here's the prover, here's the verifier. The prover is computing some operations on the ciphertext. So everything that is with the lock, it's like a ciphertext. And he's sending some oracles to the verifier, who does some stuff to check it. So what are the good news? It's that all the operations done by the prover are linear combinations of ciphertext. What are the bad news? Is that the coefficients of these linear combinations are random elements from the plaintext space. So this is basically as bad as doing ciphertext multiplication because this plaintext space is big. So there's a bunch of different optimizations that we do in order to deal with this. So first of all, we reduce the depth of this of FRI. So you do like folding, and then you fold the previous function, and then you fold the previous one, and so on and so forth. And it's like plaintext ciphertext operation, but the coefficient is very big. So this is bad. It's additively deep, but it's basically as bad as multiplicatively deep. So we reduce the depth here to be depth 1. We also improve the encoding algorithm. So we need to put these things into like the form of like a Reed-Solomon code. So we have like a shallow encoding into Reed-Solomon codes. Another thing that we do is what we call tensoring. So whereas the homomorphic encryption scheme is working over like the direct sum of it's with several copies of FP, for some reasonably small P, Fry needs to work with a pretty big field. So Fry needs to work with a field that has 256 bits. So what we do is that Fry is going to work over an extension of FP, whereas we can keep the homomorphic encryption scheme working over the smaller base field, like several copies of that. And another technique that we have is about reducing this query blow-up that was very problematic for zero knowledge in particular, but also in general, because every time the verifier is checking things here, actually he only needs like 2 elements for each of these checks. So, you know, and you're packing a lot of things here. You're packing between 2 to the 11 and 2 to the 17 elements. So we have a series of optimizations that appeared in the previous literature, but we put them together, and we reduce this blow up from this like 2 to the 11 or 2 to the 15 to like 2 to the 5, the 5th. So this is good because now we also make the verifier we make also decryption cheaper for the verifier, so the verification algorithm is now also faster. Okay, and this is a slide about our implementation. I have some numbers here on my laptop, if I can get those. And we have we need to update the ePrint to include the link in there. So the operation, the implementation will be open sourced. We were a bit ashamed a month ago, but now we're proud of it, of sharing the code. Okay, let me see. What can I say about this? Well, before I get into the actual numbers. So these are 2 different sets of parameters for Fry, basically. Fry 3 is optimized for the verifier, Fry 0 is optimized for the prover. These match some tables that we already have in the paper. And then we also have single-threaded versus multi-threaded. Okay? So when we optimize for the prover, we can get some very nice memory consumption, which is one of the aspects that can be pretty problematic when you start scaling this. So, you know, for this range of polynomials from degree 2 to the 6 up to 2 to the 11, we have memory between, you know, 1 gigabyte and 7 gigabytes. And verification is still pretty fast, even if we optimize for the prover. So it can take between, like, you know, 180 milliseconds and 340. If we optimize for the verifier, verification is super cheap. It's like 100 milliseconds at most. But now we start having a lot of more memory requirements for the prover. And if we go over here, for example, for polynomials of degree 2 to the 11, this is Fry 3, multi-threaded. Okay, this is why I need the numbers. Sorry, one sec. Yeah, well, anyway, it's not important. These are details that you can check on the paper. And yeah, I don't know how I did with time, with all the problems with the slides, but I'm happy to, maybe let's get a more interactive discussion. Yeah, thank you.
Very cool. So I think on slide 19, you don't have to go back, but it said something like there was FP.
Yeah.
You had the finite field, then you extended it to FP to the D, which was 256 bits. So that P is the plain text modulus, yeah?
Yeah.
Okay, right. So if I wanted to move this to TFHE, and my plain text modulus is a power of 2, can I just go Galois ring the whole thing, and it all just applies because Galois ring theory just generalizes Reed-Solomon codes?
Yeah. That's a good question. Fry has not been generalized to work with Galois rings. It should work.
It's just
it should work.
Reed-Solomon codes, yeah?
It
So
should work,
yeah.
but it has not been done. It should work. But someone has to do that work. Yeah.
Okay. Open problem for students then.
Open problem for students are always good. Okay, so I don't see any other question. So good. So we are almost back on. Is there a question from the back? Yeah. I was about to say we are almost back on track despite starting the section late. But
I'm so sorry. When you're providing the oracles and checking, like, when the verifier is running, they are computing the result of a consistency check on an oracle that is in the form of a ciphertext.
Mm-hmm.
Does that affect the security model, since you I guess this would be a side channel question more so than a direct security model, but, like, for example, if you implement a verifier that terminates as soon as they detect an inconsistency, presumably that leads to some disclosure about the underlying plain text. Is that something that you've considered in your model, or is it, like, out of scope?
So, okay, like a couple of things. Our whole system is non-interactive, so there's not such a thing as like I stop as early. I mean, you could do like a constant time thing, or like wait for a given time and then I tell you whether I abort it or not. It depends on your system as well, right? Do you have some sort of verification oracle for the prover? Depends on what you're implementing, and yeah, that could lead to some leakage. We're aware of this. This happens in pretty much all of the applications of homomorphic encryption, right? And there's different countermeasures that you could take. You could make keys longer, you could change your keys, and also probably for like an outsourcing scenario, your plain text space is not tiny. So even if you learn like a bit, or with, you know, the expected leakage is 1 bit, right? There will be one oracle. So you can probably live with that in many applications.
Okay, thank you.
Yeah.